got you. Wherever you want it from, we got what you need. Toilet online class, we got you.
Good day, everyone. Once again, you are welcome to Toilet online class. Just as I've introduced the set of numbers. So the first set of numbers. The first set of numbers are called the natural numbers. The natural numbers. So denoted, this one is denoted as n, as we have it on the bottom. Good day, viewers all over the world. You are welcome to Toidel online class. So today we want to look at group theory. Group theory. For us to be able to have in-depth understanding about this concept, the knowledge of the following concepts will be required. The first one is to have proper understanding about the sets of numbers. Then you must also have proper understanding about set theory. Then you must have proper understanding about binary operations. Binary operations, then you must also understand mapping, have proper understanding about mapping. So all these concepts, I've treated all these concepts in the past. So if you want to know more about set of numbers, just check my video on set of numbers. If you want to know more about set theory, I have 2 videos on set theory. If you want to know about binary operations, then you also check my videos on binary operations, then also mapping. So set of numbers, there are 6 set of numbers. Just go through what I've done there. Set theory, we know that we denote a set with capital letters, an element of a set with small letter. Then under binary operation, there are 6 properties that we discuss under binary operations, and those 6 properties are actually important, and they are necessary for us to be able to understand the concept of group theory. Then mapping will also help us as we proceed in this topic. So I have videos on all these concepts. So try and go through the videos. Then you will have proper, that will serve as the foundation to this concept, group theory. So under group theory, it depends. In some textbooks, you have just 3 properties that we check under group theory, but in some textbooks, there are 4 properties. But the most important thing is for you to understand the concept. So I'm going to introduce the first one, the first concept under group theory. That is what is called a groupoid. How do we define a groupoid? If you have a non-empty set, let's say you have a non-empty set G, where G, we denote a set by capital letter, an element of a set by small letters. So if you have a non-empty set, then let me say this. Under group theory, you also will be talking about set. The sets under consideration must be non-empty. A non-empty set is a set that has an element, at least an element in that set. So the set must be non-empty. So if you have a set G, a non-empty set G, which is closed under a binary operation asterisk, this set must be closed under a binary set, binary operations asterisk. Say asterisk, then this set is called a groupoid. It's called a groupoid. It is called a groupoid. It is called a groupoid if for all A, B that belongs to that set, we can have A asterisk B that also belongs to that set G. So what is the meaning of this? We want to establish the first concept under group, which is called groupoid. How do we define a groupoid? Groupoid is just talking about the closure property that we have under binary operations. That is, if you have 2 elements, A and B, that belongs to this non-empty set G, Then in under group theory, there must be a set and an operation that we are going to operate on every element of that set. So in this case now, G is the set, asterisk is the operation. The operation could be positive, it could be negative, division, it could be multiplication, it could be any, we have so many operations in mathematics, but we decide to represent that operation as asterisk here. So if for all, this is symbol for all elements A B could be any, it could be any element. AB that belongs to G. A asterisk B must also belong to G. And that is the definition for a groupoid. In other words, a groupoid is a set which is closed under a binary operation asterisk. So in this case now, we can say, in other words, a groupoid is a set non-empty set G, which is closed under this binary operation. So if you can get this, then that is the definition of a groupoid. That is, it shows that if you pick two elements here and you performed an operation on these two elements, we can still find that element in G. Let's take example of a groupoid. We take examples. Let's say examples. I'm going to explain one or two. When we have natural number under addition, is a groupoid. When we have integers under addition, is a groupoid. When we have rational number under multiplication, is a groupoid, etc. That is, what am I talking about? A natural number, the set of a natural number is well ordered. Well ordered, it says that we know the starting point, that this is 1, 2, and so on. Natural number, they are the positive whole number, counting numbers. Then under addition, that is any number that you pick. Let's say we pick 1 plus 4. What is the answer? 5. 5 is still part of this set. 5 belongs to a set of natural number. So natural number under addition is a groupoid. But under subtraction might not be a groupoid because natural number does not have negative. So natural number under addition is a groupoid. Integer under addition is a groupoid. In case of integer, it consists of negative whole numbers, 0 inclusive, then positive whole numbers. But under addition can be a groupoid. Because if you say, in this case now, let's say we pick -3 is a set under integer. Then +2. This also is set under integer. -3 plus 2 is what? -1. -1 belongs to set of integers. So integers under addition is also a groupoid, because any element that we pick here, we are going to find it here. Any element that we pick here will be found in integer. You understand? So when you have, just like the general definition that we gave now, a non-empty set G, in this case now, we call that non-empty set a natural number. The binary operation asterisk is regarded as positive here. So any operation you perform with this operation, with set with the elements that you have here, we must find the result in natural number. And these are the two examples that I've given. When we have 1 and 4, 1 and 4 are elements under natural numbers. If the binary operation now is addition, 1 plus 4 will give us 5. Any number that we pick from, even if you say 1 billion plus 1 billion, it will still be a natural number. Okay. Under integer now, integer comprises negative whole number, 0, and positive whole numbers. So if you say 0 plus 8, it will still give us 8. 8 is still a set under natural numbers. So these are examples of a groupoid. The examples of a groupoid. So that is the first concept that we discuss under group theory. That is groupoid. Groupoid is the first. Groupoid is just telling us about the closure property under binary operation. As I've said earlier on, please, for us to be able to understand this concept very well, this concept of group theory, please go through my videos on set theory 1 and 2, set of numbers, check binary operations. There are 6 properties there that must be you have to read it and you understand it very well for you to be able to understand this group theory. Then as we proceed, the knowledge of mapping will also be required. So please go through my videos on those concepts. The second one is called the semi-group. Before we can define it, it's called the semi-group. So what do we mean by this semi-group? Under semi-group, we also said, under this semi-group, how do we define a semi-group? We said let G be a non-empty set. This G must be a non-empty set. And asterisk, a binary operation divine on G, such that, this is symbol for such that, Roman figure 1, such that For every element AB that belongs to G, we can find A asterisk B in G. That is the first property that gives us the definition of a groupoid. Then there's another property here, second one. Asterisk is associative. Associative in G. That is, what do I mean by that? For all A, B, C that belongs to G, for all A, B, C, and G that belongs to G, we can have A asterisk B asterisk C that will be equal to A asterisk into bracket B asterisk C. That is, we are talking about the associative properties. That is why I said if you go through my videos on binary operation 1 and 2, for you to be able to understand this very well. So when we define the first concept here, which is called the groupoid, it is only the closure property that comes into being. Now we want to define the semigroup. In case of this semigroup, now we are given a non-empty set G and a binary operation defined on this non-empty set G asterisk G comma asterisk. Now this G comma asterisk will be a groupoid if only this one is satisfied, is closed. But in case of semigroup now, there are two things that we check. We check for closure property. We also check for associativity. So in this case now, if you are asked to define a semigroup, just you tell us that given a non-empty set, you can define it as any letter. It must be a capital letter because we denote set with capital letter. An element of a set is small letter. So we say let G be a non-empty set and asterisk or any symbol, a binary operation defined on that G, such that for the first condition must be for all AB that belongs to G, A asterisk B must be in G. That is closure property. Then the second property now that will give us a semigroup is that asterisk is associative in G. This is the concept of associativity in binary operations. That is, if you pick first two elements of G and we get the result, now operate with the third element. Are we going to get the same result as first picking the last two elements, now operating with first element? If you are going to get the same thing, then it simply means that G is associative, asterisk binary operation is associative in G. So if these two properties are satisfied, then we refer to G comma asterisk as a semigroup. That is a semigroup. So we must note that if the two properties are satisfied, then asterisk is said to be associative, and that is what we are going to have. So in other words, we are saying that a semigroup, in other words, we are saying that an associative groupoid, that's another definition. We are saying that an associative groupoid is called a semigroup. That is, if you have a groupoid, that is closure property, we now perform the second operation. We now have the second property, associative. Then associative groupoid is referred to as a semigroup. That is what's the semigroup. A semigroup is an associative groupoid. That is, you test for closure property, which is groupoid, then you test for associative property. So if these two properties are satisfied, then the set G and the binary operation is called a semigroup. So let's see examples of a semigroup. Let's see example of semigroup. So Z, that is under addition, integers under addition is semigroup. So that's an example. Integers under multiplication is also a semigroup. Then natural numbers under addition is also a semigroup, etc. So we can have so many examples. Of semigroup. That is, let's check the first one, integer under addition. So let's pick three elements. Let's say we have -8, 4, and 0. These are elements under integer. These are three elements. So if we pick any of these two, maybe -8 plus 4, it's going to give us -4. It belongs to integer. Let's pick 4 plus 0. Which is 4. It belongs to integer. So closure property is satisfied. So we know that closure property is satisfied. Then the second one, let's operate now. Let's pick the first element. Let's say -8 plus 4 into bracket plus 0. Are we going to get the same answer as saying -8 plus into bracket 4 plus 0? If we are able to get the same answer, it shows that that addition is associative. It's associative in Z. That is minus 8 plus 4, that's minus 4, plus 0. Is it the same thing as minus 8? 4 plus 0 plus 4. So this is minus 4. Is it the same thing? Yes, that's minus 4. It shows that integers, it is closed. It shows that integer under addition is closed. Then integer addition is associative in Z. So that simply means that integers under addition is a semigroup. So integer under addition is a semigroup because we are able to show the two. We are able to show the two properties. So integer under addition is a semigroup. Why? Because we are able to show the two properties. So that is that about a semigroup. Then I will introduce the third one. Let me introduce the third one, which is called the monoid. So the third one is called the monoid. Monoids. So in case of a monoid now, there are three properties that we are going to check here. That is, let's say we are given a non-empty set G. We are given a non-empty set G and a binary operation asterisk. So G and a binary set, G is a non-empty set. Asterisk is a binary operations. Then G comma asterisk is a monoid. It's a monoid if the first property, if for all A, B that belongs to G, we can get A asterisk B in G. That is the first one, the closure property. The second property is that for all A, B, C that belongs to G, we can have A plus B plus C to be equal to A plus into bracket B plus C. That is associative, A asterisk. This is asterisk. That is, asterisk is associative in G. So this additional property now differentiates between monoids and semigroup. That is, in this case now, we say there exists E, an identity element that belongs to G, such that for all A that belongs to G, we can have A asterisk E, which is equal to E asterisk EAA, and it's equal to A. That is, look at, in case of a groupoid, it is only this one that we talk about, closure property. In case of a semigroups, we talk about closure property and associative property. Now, in case of a monoid, there are three properties that we are going to check. We check for closure property, we check for associativity, we now check for existence of identity elements. So that is, there exists E, where E is identity element that belongs to G, such that for all A that belongs to G, A asterisk E is equal to E asterisk A, and it must be A. So this E is a neutral element. It does not have effect on the results. So another word for identity element is a neutral element. Please, there is need for you to go through my videos on binary operation 1 and 2, so that we understand these properties very well. Once you understand binary operation very well, you understand set theory very well, then a set of numbers, you have little or no problem on group generally. So once these three conditions are satisfied, then we say G comma asterisk is a monoid. That is another word. In other words, we said a semigroup with an identity element. A semigroup with an identity element is called a monoid. That is, if you are to define a monoid, just say a monoid is a semigroup with an identity element. Of course, in case of semigroup, there are two properties. Then just add existence of identity element to it. It becomes a monoid. So let's see example of a monoid. Let's see the specific example of a monoid. So examples of a monoid. Integers under addition is a monoid. So integer under multiplication is also a monoid. Rational number under multiplication is a monoid. Natural number is also a monoid. So there are so many examples under. Well, I'll just test one for one. That is, in this case now, I will say, let's say integers under addition. How do we call this a monoid? The first one we test for closure property. That is, let's pick two elements, maybe minus 4 and 5. So minus 4 plus 5 is going to give us, that will give us 1. 1 is belongs to a set of integers, is a monoid. Then the second one, let's pick three elements, say -4, 5, and -2. So in this case, I want to test for associativity. If we say -4, -4, -4 plus 5 into bracket plus -2, will it be the same thing as if we pick -4 plus into bracket 5 minus 2? So this is -2. So don't let me waste time. In this case now, we have 1 minus 2. Are we going to get the same thing? This is -4 plus 5 minus 2 is 3. 1 minus 2 is -1. -4 plus 3 minus 3. So it's also associativity is satisfied. Then the last one is that when we pick any element here, are we going to get it as a neutral element? That is the third property. Please note that under addition, the identity element under addition is 0. And the identity element under multiplication is 1. That is, anything you add to 0 will retain its value. Then anything you multiply with 1 will retain its value. So under multiplication, the identity element is 1, while under addition, the identity element is 0. So in this case now, we say is 0 plus, pick any of this number. Is 0 plus 5. It's not the same thing as 5 plus 0. And it's going to be 5. That is, this 0 does not have effects on the number. That is the meaning of existence of identity elements. So with what we have done now, we have been able to show that integers under addition is a monoid. So what's a monoid? A monoid, a semigroup with identity element, is called a monoid. So we'll now go to the last concept, which is a group. We want to define a group. A group. So how do we define a group? Of course, under a group also, we are going to have a non-empty set, given a non-empty set G, and a binary operation asterisk. Then G, asterisk is called a group. G, asterisk is defined, is a group. It's called a group. It's called a group if Roman figure 1, for all elements A, B that belongs to G, we have A asterisk B in G. The closure property must be satisfied. That's the first thing. The second one, for all A, B, C that belongs to G, we must have A asterisk B asterisk C that's equal to A asterisk into bracket B asterisk C. So the associativity must be satisfied. The third one is that there exists E that belongs to G, such that for all A that belongs to G, we can have A asterisk E, which is equal to E asterisk A, and is equal to A. That is, there must be existence of identity elements. If these three conditions are satisfied, it is called a monoid. The fourth property that will be added now to get a group is the presence of the inverse element. That is, we now say for all A that belongs to G, there exists A inverse that belongs to G, such that A asterisk A inverse or A inverse asterisk A must give us identity. That is, we are going to add existence of inverse elements to a monoid to be able to get a group. So in case of a group now, there are 4 properties that we check. We check for closure, we check for associativity, we check for existence of identity elements and existence of inverse elements. So if these 4 properties are satisfied, then G asterisk, but this binary operation G, asterisk is called a group. It's called a group. So in case of a group, there are 4 properties that you check. We are going to check for 4 properties. In other words, a monoid, in other words, a monoid in which every element has an inverse is called a group. That is, if you want to define a group, just say a group is a monoid in which every element has an inverse. So when we test for monoid and we test for existence of identity inverse element, then it becomes a group. So G, this non-empty set with binary operation, this is called a group if these 4 properties are satisfied. So let's just see example of a group. Let's see example of a group. So let's see example of a group. Specific example of a group E.g., example of a group are integers under addition is a group. Rational number under addition is a group. Then real number under addition is also a group, etc. So let's check for natural number. The first property is closure property. Let's pick, rational number as if it can be fractional, a number that can divide as A over B. If we say we have half, then plus 1. Half plus 1 is 1 and a half. That's 3 all over 2. It belongs to rational number. So it shows that these two elements, it shows that closure property is satisfied. The second one, if we say half plus 1 into bracket plus 2, is it the same thing as you saying half plus into bracket 1 plus 2? Are we going to get the same answer? Let's check. This is 1 and a half. 1 and a half plus 2, that's 3 and a half. Then this is 3, it's also 3 and a half. 3 over 1 over 2. So associative property is also satisfied. Then the third one is that under addition now, the identity element is 1. The identity element is 1. Let's say we pick 2. 2 plus 1, the identity element is 0 under addition. 2 plus 0. Is it the same thing as 0 plus 2? It gives us 2. It shows that 0 is the neutral element or identity element under addition. 0 is the neutral element or identity element under addition. And we have been able to show that. Then the last one is the inverse element. Look at, we have what we call additive inverse. 2 plus minus 2 will give us 0. So the negative of a number is the additive inverse of that number. So in this case now, if we have the element 2, the additive inverse of element 2 plus it will be minus 2. Or let's say we have minus 2 plus 2. We are going to get 0. That is the condition. If you want to test for identity element, when we pick an element with the identity, we must get a neutral element. When we pick an element with the inverse, the result will be the identity element. So in this case now, 2 plus, that's minus is plus, is minus. 2 minus 2 is same thing as minus 2 plus 2. We are going to get 0. So since we are able to test for these 4 properties, it shows that rational number under addition is a group. Rational number under addition is a group. So we have been able to test for the 4 properties. So now I will introduce the last one, the last concept. Then we call it a day. The 5th one is called the abelian. It's called the abelian group. So another word for abelian group is called commutative group. It's commutative group. That is, when we have a group, just add the property, commutative property to that group. We are going to get commutative group. That is under abelian group. Abelian group, a group G, asterisk is called an abelian group or commutative group if the binary operation asterisk is commutative. That is, you just add commutative property to the 4 properties that you have. That is, if you have tested for the 4 properties, you just say for all A, B that belongs to G, if you can find A asterisk B, which is equal to B asterisk A, then it is called an abelian group. Just like the example I gave the other time, where I said, the example I gave the other time, we just say when we pick 2 elements in that group, say we pick 2 elements, 2 plus, let's say 2 and a half. Is it the same thing as half plus 2? Yes, this 2 and a half, and this 2 and a half, 2 and a half. Then that simply means that this G asterisk A is an abelian group. Abelian group simply means the 4 properties. Just check for the 4 properties of a group. Now add commutative property to it. Then you get an abelian group. Then the example of abelian group. Example of abelian group is are the following. These are the example of abelian. You can actually check Z under addition is an abelian group. So rational number, a real number under addition is an abelian group. Rational number under addition is an abelian group. So at times, what about Z under multiplication? Will this one be an abelian group? Will it even be a group? Just go ahead and check. Once you check, once there is one once there is one negation out of the properties that we are going to check, just pick one notation, negation that will cancel it out. Then just conclude that it is not a group. So I would love to stop here because of our time. We continue from there some other time. Thank you for listening, and God bless you all.
Mathematics is made easy, no more fear. Target online class, we got you. Wherever you want it from, we got what you need. Target online class, we got you.
Good day, everyone.